All right, welcome back, Count 2 students. Those of you who chose to take the makeup quiz, I hope it went well for you. Should get those graded before too terribly long and get your grades adjusted accordingly. Today I want to talk about the first section of chapter 12. Maybe you noticed by going straight to polar coordinates, we skipped that first section. I think as it turns out, the calculus professor whose videos we've been relying on didn't make a video over section 1. And I think there's some important things in there. In particular, I think there are some important things that, that you'll run into in Calculus 3. So if we can get you a little bit familiar with it now, you'd be a little bit ahead of the game whenever you take Calc 3. Just like polar coordinates, we'll break it into 2 days. Today we'll talk about the mechanics of the topic. The topic is parametric equations, like how is it different than what we've been doing, and how can we use what we've been working on to help us determine what's going on with curves that are defined parametrically. And then the second day we'll dig into some calculus applications. And that'll pretty much finish the semester as far as new material. We will have a review for the final. I'll post some information there, but that'll be later next week. All right, before we jump into section 1 of chapter 12, I just wanted to work a polar coordinates problem. I picked one that actually I signed. I feel okay doing it because if Pearson works as it usually does, your problem will be slightly different, but maybe seeing me work through it, the problem in the book, maybe it'll help you build up more skills as we learn how to work with polar coordinates. And I should say, I think the calculus professor explained this, but let me say it again and let me say it very explicitly. Polar coordinates, they're different than rectangular coordinates. Some things are easier to do in polar coordinates and some things are more complicated. The reason why we're learning about them is so that when we have a problem that can more easily be solved in polar coordinates, that we can do it. We're not learning them so that we can take problems we could previously solve easily and make them hard. That's not at all what we're interested in. We're interested in learning how to apply the calculus we've learned to the problems we face in the best possible way. And there are some problems where polar coordinates is absolutely the best way to go. And what we need to know is, like, when is the problem conducive to solving in polar coordinates? And let me just give you some examples. I have a problem on the board we're going to work through in a minute, but let me just give you some examples. By far, the most important application use of polar coordinates is when we're dealing with circles centered at the origin. So let's think about it a little bit. In rectangular coordinates, if I want to use functions and talk about the circle, let's say we have a circle centered at the origin of radius. Let's don't call it R because that's a polar coordinate. Let's call it A. Then in rectangular coordinates, if I want to talk about the points on the curve using functions, it actually requires 2 of them. Let's say F1, but the top is the square root of a squared minus x squared. Take the equation for a circle and solve it for y, and you actually get 2 solutions, one for the top and one for the bottom. And we'll call it f2 of x, and it is the negative square root. So we can break a circle down, circle centered at the origin, into functions of x. We can do it. Those are not the previous functions. For example, if we needed to integrate, if we want to find a little slice of area, the antiderivative is not obvious. We learned a technique for it earlier, trig substitution. Like, yeah, I heard a few groans there. It's hard to work with. But we can do it. We learned how to do it. We can do it if we need to. But in polar coordinates, we can describe the circle with one function, and here it is. r equals a constant function. So this guy in polar coordinates does this exact same thing that these guys do in rectangular. So you don't have to be a rocket science to understand that for these guys right here, circle center at the origin, polar is far superior to rectangular coordinates. Okay, so that's maybe the most extreme example I can give you. Complicated functions, trivial functions, same curve. Polar is super wonderful. It turns out that polar is the right way to go, possibly, but as polar has good representations for these three curves. The one we just talked about, circle centered at the origin. I'll write the origin as 0, 0. The second curve are circles that pass through. The origin. So I haven't said so much about these. Maybe someday we can work on it, or maybe better, I can find an assignment and you can work through it. And the third one are lines. The third one is lines that pass through the origin. If lines don't pass through the origin, then they're not very pretty in polar coordinates. Now that would be another good assignment, to figure out what a polar function is, a line with slope m and intercept b. But I'm not going to talk about it here. I'll let you think about it. You know, maybe I can find a good assignment and ask you to do it. In general, these are the three kind of curves where polar has better representations. The first one, like we said, is r equals a constant. The third one is theta equals a constant. Whatever the angle is, I'll call it theta 0. If a line passes through the origin, then it has an angle of elevation, and that's the theta value. And all points on that line have that same theta value once we learn how to handle negative r's. All right? Now, the other thing polar got us was curves that we never saw before in rectangular coordinates. So it can open up a new area like cardioids and limasones and spirals that we never saw in rectangular because they're just too awful. But in terms of commonalities, like if I have a problem and I need to decide, do I want to do it in rectangular coordinates or in polar? If these curves are present, then the very first thing I should think about is polar coordinates. All right, like I said, I want to solve one problem. And I've got it written on the board over here. This is number 53. I think I said this is part of your assignment. I assume that Pearson will give you a slightly different version, but I wanted to work through it just to give you a little more information that you can rely on. So the problem says, find the area common to the circles. The problem tells us these are circles. We'll believe them. We're not trying to figure it out. The first one is r equals 2 sine theta. The second one is r equals 1. The second one is obviously a circle. We talked about it over there. It's a circle of radius 1, centered at the origin. The constant r function is a circle centered at the origin. Not quite so obvious, but r equals 2 sine theta is also a circle. It's centered at the point 1, 0, and it has radius 1 as well. So it looks like my pen got a little bit crazy. These circles are exactly the same circles. One of them is just shifted down a little bit. They have the same radius. Therefore, they're exactly the same circle. And the problem says find the area common, the area that's inside both. And so I've shaded it in here. And notice there is an angle right there where the function on top below that line is 2 sine theta, right? We need to integrate from 0 up to this angle, that function, to find the area in this little sliver. And then we need to go from that angle, we'll figure out what that angle is in just a minute, up to, say, pi over 2, and that will get us the area that's inside this circle, we'll just integrate the function that gets us area under the function 1. Nice and easy integral there. And then I think, because these are circles, a lot of symmetry properties, we can just double it and we'll get the same area over here. Or I could do the analysis, I could find the angle over here where they intersect, but we'll just find the area in the first quadrant and double it. So our area looks like we're going to double it, and the formula has a 1/2. We integrate from 0 up to this angle. Let's call it theta sub 0, and we'll figure out what it is in just a minute. The function on top, so to speak, on top means further away from the origin in polar coordinates, or r, is 2 sine theta. And we know the formula says you got to square that to get area. And then we need this area over here. This is the easy integral. We integrate from our angle, which we've not found yet. We gave it a name, theta 0, and we're going to go all the way up to pi over 2. And the function on top here is the function 1. So don't forget to square it. Just joking. So we need to find the angle. At the intersection point, both curves are the same distance away from the origin, so very likely they have the same r value. So if we set those r's together, 1 must be the same as 2 sine theta. And so sine theta equals 1/2. And looky there, they gave us a really wonderful number. We're in the first quadrant. So theta 0 is pi over 6. As you know, you watched the first video on polar coordinates from the calculus professor. Every point in the plane has numerous, actually infinitely many polar representations. And there's no guarantee in general that it's going to be the same value of r. I'm talking theoretically. I don't know of any problems where that causes us problem. I mean, here it's pretty straightforward. We just need this r value to match that one, and we were able to do it. And so now let's copy our integrals over. We'll do a couple of things first. We will cancel out our 1/2. The 1/2 comes from the formula, and because we're using symmetry, we're doubling it, so that just wipes all of those out. And then we can supply the value for theta 0. So, and let's square also. So I get the area is equal to the integral from 0 to pi over 6 for sine squared theta plus the integral from pi over 6 to pi over 2, 1 d theta. So we get the trivial integral and we get one we need to work on a little bit. But remember, let's take the 4 out. I asked you to memorize the antiderivative of sine squared. I told you we're going to see it every now and then. And we've seen it every now and then. So thank goodness we memorized it. We get 1/2 theta minus, because it's sine, another 1/2 sine 2 theta. From 0 to pi over 6. And over here, we just get pi over 2 minus pi over 6. Right, the antiderivative is theta, plug in pi over 2, subtract pi over 6. Let's pull these. Let's be careful. 4 times 1/2 is 2. This 1/2 is multiplied by the whole thing, so we can combine the 4 and 1/2. We'll keep this 1/2 here. So this 1/2 is gone. Get it out of our way. It's incorporated with the 4, and then we're going to plug in pi over 6. Goes in there, and then I get minus 1/2. If you double theta, you get pi over 3. The sine of pi over 3 is the square root of 3 over 2, we know. Pi over 2 minus pi over 6 is pi over 3. Multiplied by 3, 3 pi minus pi is 2 pi over 6, pi over 3. And finally, I'll distribute that too. I get pi over 3 minus, it cancels, the square root of 3 over 2 plus another pi over 3. Let's double that. There's our answer, the area of the shaded region. All right, I hope that helps. I'm going to pause this video and then we'll set up to move to the next section. All right, chapter 12, section 1, parametric equations. And before we start, let me say what our goal is here. Just like for polar coordinates, there's a new way to talk about curves in the plane. And we discovered that there are some ways in which polar coordinates are better and some ways in which they're not so good. Okay, same is true for the topic in section 1. Sometimes parametric equations are the very best things to use to solve a problem, and sometimes they're not. So we'll talk about the mechanics of how they work. We'll look at several examples, and we'll also try to keep in mind that in the end, we really want to know when polar parametric equations are the best way to describe a problem. And a lot of this is motivated by the fact that using functions of x, the kind of curves we can study is so limited. The graph of a function of x, all it can do is flow from left to right. It can go up or down, it can go to infinity if there's an asymptote, but it can't double back on itself, it can't spiral. It's pretty limited left to right. Even though it's limited, we've been able to focus on it for almost all of the academic year here in Calc 1 and 2. It kept us busy, but now we're ready to move on. So what we hope is that these new systems, polar and now parametric equations, that we can deal with without too much trouble, more complicated curves. And I think we've seen that's true for polar coordinates. We've been able to add, very simply things like spirals and cardioids. And I mean, circles centered at the origin, absolutely beautiful representation in polar. So now let's look at another one, parametric equations. So one curve described parametrically is given to us by two functions. One function controls the behavior of the x coordinate. We'll call it x of t. And the other one controls the behavior of the y coordinate. And we'll call it y of t. A pair of those functions gives me one set of parametric equations. And the graph of that set, it's the set of all of the points. So I have t values. T is called a parameter. And for every t value, at least maybe in a particular range, I get an x and a y value. I plug that t into my functions. I calculate x and y. And so the graph of one set of parametric equations, one parametric curve, is the set of all points. I plug them in, and here's my x coordinate, there's my y coordinate, and I just consider all of those points for all of the t values for which the curve is defined. Sometimes we have a range of t values. Sometimes it may just be all of the values for which these functions are defined. But that's the idea. So let's start with a super simple example. It's not a very good example. If you remember what I said, that what we want to do is find out when parametric is better than rectangular or polar. But we got to start somewhere. So here are my functions. X equals 2t, y equals t squared. I just pulled these out of thin air just as an example. And so the idea is that I let my t take on several different values. I've chosen a handful here. And then we plug those values into my X and Y functions, and I hope I did the arithmetic right. And now we wonder, like, what does the curve look like? So if I plot these points, notice the origin is on it. When t equals 1, X is 2, Y is 1, so that gets me this point. Notice I've compressed the Y-axis a little bit because the values get larger. When t equals 2, I'm at the point 4 and 4. And when t equals -1, -2, 4. So maybe that's about right there. When t equals -2, -4, 4. Oh, I believe this calculation is wrong. When t equals -1, y is 1. Let's fix that and then drop this guy down. Nope. This guy. -4, we're back up to 4. So look at all those curves. There are infinitely many points on the curve, and we've only graphed, well, I guess I have a few more here. We could let t go out to 3, and then we're going to be out here to 6 and 9. And -6 and 9 is going to be about right there. A little bit higher, maybe. So what do we have? 7 points. There are infinitely many on the curve, but you can see a pattern starting to take shape. And we might wonder, could it be a parabola? Man, it feels perfect for those 7 points. And I'll draw the parabola in. And so, you know, is there something we could prove that's true? There absolutely is. A useful thing for us to do is, we won't do this all the time, but sometimes we can do it. We'll call it eliminate the parameter. So notice I can take the first equation and solve for t, 1/2 x. And then I can plug that into the second one. So y equals, well, y is t squared. So we're going to get 1/2 x squared, and that's 1/4 x squared. And now we absolutely recognize the equation of a parabola. So we looked at 7 points, we made a guess, and we made a good guess. It helped that I knew the answer. But that's the idea. And like I said before, eliminating the parameter kind of reduces this back to rectangular. And, you know, if that's what we need to do all the time, then probably we could just work in rectangular. So we're not always going to do that. It's just, this is our first example, and we can see, we make a conjecture, get some data, make a conjecture, and then we can prove that it's right. Okay? In the end, we're going to be talking about maybe parametric curves that we don't really think about in terms of rectangular forms. We'll see. All right, there is a simple example. Let me pause you while I set up the next one. All right, one thing I failed to mention about the last example is that a lot of our parametric curves have a direction of orientation. It's the direction of increasing t. So, I had an interruption, but I'm back now. I was saying that parametric curves have sometimes have a direction of orientation, the direction of increasing t. And if you look, when t increases from 0 to 1 to 2, we're moving from this point to that point to that point. And so this particular curve, the orientation is from left to right. And so it's customary to put arrows on the curve showing that orientation. It also sometimes is helpful to identify the t-value for some points. Since we've calculated some points, we can do that. This point right here corresponds to t equals 0. The t-values are not explicitly represented in the graph, only the x and y. So t is like a thing in the background. It controls things, but it doesn't get to show up. And then this point over here corresponded with t equals 1, and so on. Now, if you think about graphing the curve as we move through a range of t from small values to large, you can kind of visualize motion along the curve. We'll get a really vivid example of this in just a minute, but it's one of the uses that you'll make of Calc 3 in Calc 3 of parametric equations. I mean, you'll think exactly a parametric curve is the path that some object is moving on. And as t increases, you can visualize it moving. In a minute, we'll pull our calculators out and we'll get a really good example of that, I hope. But first, I have kind of a weird example just to show you that these things are different than what we're used to. So here's my curve. I've done some of the work up front. X equals sine t, y equals sine squared t. And maybe right off the bat, if we eliminate the parameter, you notice that, well, y equals x squared. X is sine, y is sine squared. So without even really doing any algebra, I can see that all of those points are going to satisfy y equals x squared. So it must be a parabola, right? Just like this one. But no, it's not a parabola. How big can x be? I mean, take a look at that function. It only goes from -1 to 1. That's all. Because x is a sine value. And then, given that, the y values, they're only going to go from 0 to 1. So what we can say is that this curve, it lies on a parabola, but it is not the whole parabola. I've calculated a few points. Here they are. When t equals 0, both are 0. Sine is 0. Pi over 2, I get x is 1, and 1 squared is 1. At minus pi over 2, I get negative 1, 1. So here they are. And now I know that they lie on a parabola. So I'll draw a parabola. And then what happens is t goes on and on and on. Again, think about it as a path of motion. Some object just kind of moves back and forth. Comes to a brief halt at these endpoints, and then it turns around and goes the other way. So again, something very different than what we ever experienced in rectangular coordinates. I can't really show an orientation because it goes both ways as t moves through some range of the real numbers. All right, so a little bit different example than whatever we have seen in rectangular. And again, I'll pause you while I set up the next one. All right, here's another example. Grab my pen. So the curves, the first two examples, the first one was shown, I chose just to show you the mechanics where the details are simple and easy to work out. The second one I chose to show you how things can be different here than we've ever seen before. The third one I'm choosing because maybe this is the beginning of the most important use of parametric equations. So the first two examples, you don't need to memorize those. You don't need to, just enjoy them. Understand how what we're doing now is different than what we've been doing. But now here's one we need to take special note, and we'll work it out here. And then we're going to generalize just a little bit. All right, so my parametric curve, my set of parametric equations is given by x is cosine t and y is sine t. And so, because I don't know anything else, I'm going to make a table of values. And I just pick some random values here, not quite random. I didn't want to use my calculator, so I picked good values. If t is 0, then the cosine is 1, the sine is 0. We're at the 0.10, there it is. We could write the t value there. Now I picked pi over 4 because sine and cosine have the same value there. 1 over the square root of t. My calculator says that's about 0.7. So it's a little bit closer to the origin than this point is. This one's 1 unit away, and this one is 0.7. But it's on this 45-degree line. And then I went all the way through the first quadrant, pi over 2. And then, of course, x and y flip around. The cosine is now 0, the sine is 1. Now, how do you think the points get from here to there? Excuse me. It appears they're following some curve. And what might that curve be? Could it be a circle? I only drew the first quadrant. You know, we could make table values to go on, but like I said before, you know, using a table is pretty primitive, and we'd like to get, you know, some more sophisticated ways to analyze the curve. It's where we start because, you know, what else did we know? But we'd like to find other ways to do it. So what I want to think about, is it possible that these equations could be defining a curve that happens to be a circle? And there are a few ways I could analyze it. The simplest way is, by the way, if it is a circle, the radius is 1. And it would be centered at the origin. I know the equation of a circle centered at the origin is x squared plus y squared equals 1. We know that. Follows from Pythagorean's theorem and properties of a circle. So I know an x and a y. Let's plug them in and see what happens. So x is cosine t, and then we're going to square it. Y is sine t, and then we're going to square it. And then I want to know, do those guys add up to 1? Well, look here. What we get is the Pythagorean identity. It adds up to 1. So it is a circle. And if I let t go through all of the quadrants, we're just going to trace out the rest of the circle. The graph is a circle centered at the origin. Radius is 1. The orientation, I labeled t equals 0. I didn't label the others, but clearly, I think as t increases, we're tracing this circle counterclockwise, consistent with how we learned to measure angles way back in the day. So as t starts at 0, heads into positive numbers, we just retrace the circle over and over and over. Again, it takes 2 pi radians, a value of t of 2 pi to get completely around the circle. If I let t increase, it just keeps tracing around the circle. I think it's not too hard to believe. Let's go to example 4. A cosine t and y is a sine t. I hope it's not too hard for you to believe that this is going to be a circle. If a is a positive number, let's force it. This is going to be a circle of radius r. We could prove it exactly like we did here. We get a squared over here. So the graph, now the radius is a. And the orientation is still going to be counterclockwise. If a were a negative number, we would still have a circle. The radius would be the absolute value of a. That is, we don't want to talk about a negative radius. And if a were negative, it may flip the orientation to be clockwise instead of counterclockwise. Not important. We could figure it out. I don't really want to figure it out. And maybe it'll show up in your homework. So this guy right here. I told you these examples, they are super important. This is something that every good Calc 2 student, especially when they move into Calc 3, they just know it. I'm off the top of the board. Memorize it. We don't want to have to think too hard about it. And notice for the orientation that I've suggested here, t equals 0 at this point on the positive x-axis, counterclockwise, we need cosine to be on the x and sine to be on the y. If you flip them around, then we're going to get the same circle, but it's going to change the orientation. Not a big deal. We'll just recognize that it's true. All right, so 4 examples, 2 of them just to get us started, and now a very important example. One more example. Not going to do the work here. We're going to take a guess. Let's let x be 2 cosine t and y be 3 sine t. Think a minute. What do you think the graph of that parametric curve is going to be? Compare it to the one I just erased. Compare it to that one up there. The x values go from -2 to 2. Twice the cosine. But the y values go from -3 to 3. Hopefully, you've made the decision that the graph is going to be oval, not a circle, oval shaped. Maybe you thought an ellipse. Ellipse is a reference to a very specific curve, a very specific kind of oval. But it turns out it's the one that we get from these equations. So not too much trouble. I think we can believe, like I said, the x's are going to go from 2 to -2. The y's are going to go from 3 to -3. And so we're going to stretch, oops, couldn't see my 3 at the bottom. So we do get an ellipse. And because my coefficients are positive and I put cosine there, the orientation will still be counterclockwise. Okay, so start with the circle, make one little tweak to it. We pause to say this is an important case. This will be on the final. A circle defined parametrically. I'll guarantee it. And then, given what we learned here, then I think it's pretty easy for us to make a little adjustment and figure out what's going on. At the very least, you can tell it's not a circle because you can think of the range of x values on the curve from -2 to 2. The diameter, so to speak, is 4, but in the other direction it's 6. Like, well, that's not a circle. That's not even a diameter. I think there are words for those, but save them for another day. All right. I have next a very, very interesting example. It's not important so much. I'm not going to ask you to memorize it. It's important because it shows us that there are even still more weird things, cool things that can happen with parametric curves that we could never even think of for rectangular curves. I'm going to set it up, and while I have it paused and while you have it paused, go get your calculators because we're going to do this next one on our calculators. All right, hopefully you have your calculator ready, and you'll want to pause this video as you do what I'm asking you to do. First of all, make sure you're set up in radian measure for angles, not degrees. If you've been in physics lately, maybe you have it in degrees. Everything we do here, we measure theta in radians. So make sure that's done. And then you need to change the mode of your calculator. You need to change it to parametric. My calculator, I have a TI-89, and there are 3 graphing modes. There's rectangular, what we've been in most of the time. It also has a polar graphing mode, and then it has parametric. So however you do that for your calculator, figure it out and change it. Pause this video while you're doing that and then come back. All right, so hopefully now you're back. In order to get a good viewing window for the graph that we're going to draw, I notice that x and y are sines and cosines, so they range between -1 and 1. So let's just set our window up so we can use the full screen. X will go from -1 to 1. My calculator, there is a window button, and you have the capability. You may need to hunt around a little bit to find it, but you can set your x values to go from -1 to 1, the same for y. And then we need to also set our t values. We could be scientific about it and figure out a good t. I just did it by experiment, trial and error. And it turns out for this example that if t goes up to 7, we get to see the whole curve. So set up your t value to go from 0 to 7. And then there's another interesting variable inside your window command called t-step. It may be called delta t for some of your calculators. Basically, the way our calculators graph a curve, they don't analyze it, look at the algebra and say, oh, that's a circle, and draws a circle. It calculates points on the curve and connects them with a straight line. Okay, for us to do it that way, it's horrible. But for the calculator to do it, it can calculate so fast that it's pretty efficient. So t-step controls how far apart the t-values are. And once we get done with this example, you should play around with it. In fact, maybe I'll do an example at the end and I'll show you for this very same one, if we get a bad t-step, that it changes it very much. We want t-step to be small. So, the smaller it is, the finer, the more points it's going to graph, the finer the resolution, the better we can see the graph. If you go too small, it goes super slow. And this is also a good example to illustrate what I talked about before. That is, you can think about these parametric equations as describing the motion of a particle. And you'll see very much, if you get a smallish t-value, you'll see the curve actually being drawn on the screen. And you can imagine, being at a carnival and being on some ride, moving along with the calculator as it calculates these points. So get that all set up. And then you go to, once you have it set up on parametric mode, you'll notice, this is how you know you're in parametric mode. It will ask for an x equation and then it'll ask for a y one. It'll allow you to graph more than one. So maybe the first one is x1 and y1. Those go together. That's where you put our functions. And of course, on the calculator, the parentheses are going to show up. And once you get that all set, then you're ready to graph it. Okay, so get ready to be impressed. So hit your graph. I'm going to hit mine and I'll show you. So pause it until you get an interesting graph. If it's not interesting, something's not quite right. So I'm going to graph mine, but you pause the video until you get yours and then we can compare notes. So let's graph this thing. Okay, I need to. Oh, that's okay. I'm going to show you the finished product. It's not going to be tracing it out, but it's what it should look like. And when you see yours graph, you can watch it move along through as it works its way. So that's the graph that I get. A thing of beauty, isn't it? Can you imagine describing those curves with functions of one variable? Yeah, neither can I. Okay, now let's play around with t-step. So I'm going to change mine. Everything else is the same. I'm going to change t-step to like 0.1, a fairly largish value for this calculator. And see if I can hold this up so you can see it, trace it out. So it's going pretty fast. And bingo, there it's done. Okay, now let's make a super small value of t-step. Not sure I have the patience, but let's go 0, 1. And again, now notice it's going to go slower because it's calculating more points. Might not want to go smaller. This is 0.01 on a TI-89. So T is going, remember, up to 7. And it turns out that 7 is big enough to get all the curve drawn. There, just finished drawing the curve, and now it's done. It's gone all the way up to 7. The last little bit of the range up to 7, it's retracing. Now, what happens if we make t-step way too large? So let me make it, I don't know, 1. And then I need to crank my Tmax up. If Tmax is 7, and t-step is 1, it's only going to graph 7, maybe 8 points, and I want to graph like a bunch of them, so I'm going to punch it up to 500 just because this is going to be pretty crazy. So here's what happens when t-step is too big. Remember, it's calculating points adjacent t-values as determined by t-step, and then it draws a straight line. So if t-step is too big, like, oh, look at that curve. What? It's just total chaos. And it's still working. I think right over there, that busy should go away when it's got all 100 of them applied. There. So there are some semblances to the graph we got, but it's like totally worthless. So there's a sweet spot for t-step. See if you can find it on your calculator. 1 is definitely way too large. All right. I think I'm going to pause and post this video. Remember at the beginning I said today, our first day in this section, we're talking about the mechanics of it. And then this video prepares you for the assignment that will be due on Monday. And then on Monday, we'll post a video that will prepare you to do the assignment due on Wednesday. And that's where we apply some calculus to these parametric curves. All right. So if I feel like I got everything in this video, you should be good to go to do the person homework. If not, I'll send out an update one way or another. All right. Happy problem solving.